Thank you very much. So thank you to the organizers for putting together a lovely program. Even though I'm only here for the short time this week, I'm happy to get to step into this community for a minute and chat with everyone. So thank you very much. I apologize again for messing up the schedule this morning. In case anybody hadn't heard, our toddler fell and broke his arm this morning, so we were at the hospital getting a cast this morning. As was just said, I'd like this to be interactive. I was asked to do an introductory lecture, so it's possible that what I prepared everybody knows already and you want to talk about something else. So consider this very flexible, and I'm happy to expand or go in different directions as everyone desires. So the goal of today, when I was thinking about this talk, when people were talking about things that they were interested in for this program, lots of people said non-geometric constructions in string theory. And this is going to be a talk very much about geometric constructions. But I wanted to sort of anchor in as broad a way as possible what we understand about some of the geometry of string dimensional reductions. I'm going to try and actually do this in a setting that isn't tied to any particular construction, so not heterotic F-theory, but just in general, what do we understand about the geometry, and where have we made some progress in trying to bound, classify, characterize that geometry in recent years. So to put this in context, I wanted to share an anecdote. So I co-organized a program at KITP in Santa Barbara for the first 6 months of this year. And the goal of that program was very broad. So it was trying to sort of address all possible areas of string theory and get different subfields to talk to each other. And so I sat through lots of talks on topics that I don't normally, in the conferences I usually go to, get to hear. And a refrain was given in numerous talks that I heard on the more formal side of our field, so a lot of holography talks. Someone would start their talk and say, a long time ago in string theory, we used to think that we were going to find the right Calabi-Yau, and we'd write down some physics that looked like our universe. Ha ha ha, we all know that's really dumb. And thus now we should work on holography, which I think working on holography is excellent. But it is a legit question, right? Maybe not one Calabi-Yau, maybe not string, maybe non-geometric constructions. But do we feel as a field that we're ready to give up on trying to get the real world out of string theory? I think this community, certainly String Pheno last week, and people at this workshop, we're still interested in the answer to that question. I personally, if somebody could demonstrate to me right now that it isn't possible to find solutions of string theory that look at all like our universe, I would probably choose to work on something else. For a lot of people, that isn't the case. They feel like string theory is still a really interesting arena with which you can play with general ideas about quantum gravity, which is a perfectly legit goal. But the question I want to sort of address today is, if we are interested in solutions that lead towards the real world, how do we go about answering the question, can string theory do this or not, right? And if the answer is no, we want to know that too. We want to be able to be as exhaustive and complete as possible. So we want to ask, does string theory contain, I'm going to be very broad here and say Pheno solutions. What kind of Pheno? Well, obviously, if we're super ambitious, we want all of particle physics and cosmology. Maybe we want other toy models as well. If we think that the refrain from the 80s, where obviously things were too ambitious, maybe we don't think that there's some one golden construction of string theory that leads to exactly our universe out there. The question is, what is the alternative? So I'm going to focus within string compactifications. So i.e. geometry. We want to ask the following questions. So first one is, what is possible in as broad a context as we can? So what kinds of effective field theories can we get out? And the big obstacles, of course, and the reason that people are expressing doubt about whether this is a tractable problem is this just too big a question? So are there simply too many geometries to scan over? Can we actually answer this in a systematic way? I feel like the vibe in some parts of the community is, there's 10 to the many, 500, 50,000, whatever number you want to do, 10 to the really huge number of geometries. We'll never scan over all those. Maybe there's some solution out there that looks like our world, maybe not, but how are we going to decide, right? So there are a lot of systematic approaches to this. So there are big scan projects underway. For example, looking for de Sitter vacua by the Cornell group. The work that Miriam talked about is one example of this, searching for standard models. Waddy Taylor's work understanding, generic gauge groups in F theory. All of these are, big systematic scans. There are techniques in machine learning that people are beginning to implement in terms of trying to scan over lots of the landscape. And then, of course, there's the question of, let's say, better control. So I want to be a little bit more precise about what I mean by that. In string theory, if we start with higher dimensional string theory, so say 10D string theory, we have some black box of string compactifications that leads to 4D physics of our choosing. And the major obstacle in the last 30 years of string pheno and onwards is that we have poor control over this black box, right? It is an extremely labor-intensive process to turn the crank and actually derive effective field theories in a controlled way to say what we get. And we don't know how to engineer these theories. So imagine that there are an infinite number of solutions of string theory. That could be the case. There's an infinite number of 4D quantum field theories, but we don't care because we understand how to write down ones that look like our universe, right? We know how to write down the standard model of particle physics. So what we really want to know is, how do you engineer this backwards? If I know the field theory I want, how do I choose the right geometry? How do I understand a priori what corner of the landscape I would like to be looking at? Now, I don't have the answer to that process, but I want to highlight a little bit about what we can say about the possible geometries that could be in play in this process, and then where we might have more tools for sort of narrowing and constraining that set down to things that are of more interest. Yeah. Correct, and non-geometric constructions are very valid. I hope there'll be other talks. Or even, asymmetric orbifolds, lots of other things that, T-folds, there are many very non-geometric constructions, and you're absolutely right. So I'm not going to claim about the only thing that's possible in string theory. One reason to look at geometric constructions, as you have in your work, is that they're at least an arena where we have some, fairly robust computational control. If we decide that this is not happening for us, right, if we can, rule things out, then of course we should look more broadly. We should look more broadly anyway, but I'm not at all claiming that this is the whole story. This is just an arena where we can try and ask this question. Other philosophical thoughts as we start here? Okay, so good. I mean, yeah, the whole, kit and caboodle of, some background geometry plus branes, orientable fluxes, bundles, all the other ingredients. But there are also non-geometric constructions that should be looked at too. Okay, so within that context, right, we want to understand, since we're in the business of exchanging geometries for effective field theories in the question above, we want to ask, within the context of string geometries, what do we know about these? So for geometries, we want to understand what are the generic solutions, generic geometric backgrounds, first at the level of a manifold and then decorated with other structure. We want to understand what dualities might be in play. So foreshadowing a bit here, of course, things like mirror symmetry. In the type 2 setting has been tremendously powerful over the last 30 years. We want to understand, are there analogs of string dualities that we haven't explored yet in the n=1 setting? That's something I'm going to return to in a few minutes. And we also want to really focus on better controlling the effective theory. So being able to read backwards, what do I need to understand about the geometry in order to read off the properties of the field theory of choice? All right, so with all that general philosophy in play, I want to just survey a little bit first about the manifolds, and then we'll talk about other structure that we might want to consider. And again, this may be all familiar to the audience. I aimed this to be introductory, so if you're feeling bored, let me know and we'll switch gears. So first, the arena for most solutions of interest for string geometric compactifications is going to be SUN structure manifolds. Specifically, if I'm doing F theory with general flux bacterians, this will be SU4 structure. We might do G2 structure manifolds. I'm going to focus on 10D solutions for a moment and look at SU3 structure solutions. So what is the idea? We want to reduce 10D to 40, and we're going to aim for n equals 1 supersymmetry. Why n equals 1? We're interested in chiral matter. Maybe we want to do, scenarios where we would like to try and, address the Higgs and the hierarchy problem via supersymmetry. Or maybe none of those things. This just happens to be an arena where we have good computational control of the effective theory. So let's focus on that to start. In this case, of course, we have to have a supersymmetry parameter that reduces the 10-dimensional supersymmetry down to a quarter to have n equals 1 supersymmetry in 4D. And so we are interested in decompositions of spinors in 10D, containing those in 4D in the standard way. So the 16 containing a 2, 4, this form. And so the spinor of SO6 is the fundamental of SU4. So without loss of generality, we can write our preferred spinor. It's going to parameterize the compact dimensions that we're trying to dimensionally reduce over. So I should say here that M10, of course, is going to be some M6 cross M4 cross X6, what I'm about to write. On a patch, we can write our preferred 4D spinor as something where we put all the interesting stuff in the final component. And the SU3 and SU3 structure comes from the fact that transition functions that would preserve a spinor of this type in general look like this. So SU3 structure because you can patch together the compact manifold in such a way to preserve a single spinor. In general, this is not a covariantly constant spinor, just a single spinor that will parameterize your 4D SUSY. Such an SU3 structure manifold, that spinor can be used to define geometric objects that are going to be important to us. So for SU3 structure, of course, we can build two things that characterize the geometry. Out of our chosen spinor, eta naught, we can build a two form, which I'm going to call Jij, which looks something like this. Right, that's a gamma 7. So here, these are gamma matrices. Gamma 7 is the product of all gamma matrices. And a 3 form, I'll call it capital omega, which I can write as omega plus omega minus in complexified form, where these guys are the following. So you can show that for these definitions of a 2 form and 3 form built out of your single, nowhere vanishing, not quite covariantly constant spinor, you can show that these two objects satisfy some identities, namely that J wedge omega is 0, and that J wedge J is minus 3 over 4I omega wedge omega bar. Here's the part that becomes more useful. So these two things are true. And then the possible SU3 structure classes can be basically defined in terms of derivatives of J and omega. So the definition here is that I write the following. Imaginary part, omega bar, sorry that I probably did my boards the wrong way around. Should have done this board first, but okay. So these two derivatives are characterized by these things that I've called W. The WI are called torsion classes. And these take various forms. So for example, W1 is a function, W2 and 3 are both 3 forms, 4 and 5 are 1 forms. So these are particular background elements In a real string compactification, whether this is heterotic string theory, type 2A, type 2B, or antifolds, you will have a set of fluxes that are turned on for your generic background, and that will specify for you a set of WI. You give me the WI, and then we have enough information to specify the covariantly constant spinner and, covariantly not quite constant. Why am I saying not quite constant? There's a D operator that's shifted by the flux background in play. If you give me the WI, then I can generate the J and omega and find the spinner eta naught, and we have a complete manifold specified. So different WI for different classes of string compactification. So as an example, let me do heterotic string theory. Here you can show from the general equations of motion, you have a single three-form flux, which can be not zero. And so in this case, the most general solution looks like W1, W2 is 0, W4 is a half W5, which is equal to derivative of something, i.e. it's exact, and W3 is free. Again, illustrating the idea here, W3 is actually fixed by the three-form flux background that you would choose in a heterotic background with flux. And this, in terms of what information is in your theory, by the Gukov-Wafa-Witten superpotential, this, of course, looks like H wedge omega. So the 4D superpotential, this is in 4D. 4D superpotential is fixed by the choice of a W3, which in turn fixes a three-form flux, and so you have a background. This is the Strominger system, or Strominger-Hull system. Sorry, yeah. Correct, yeah, so there can be like domain wall solutions, various half supersymmetric solutions. So yeah, everything is general at this point. Yes. Correct, yep. I mean, for SU3 structure, good. So I'm aiming for, this is general for n equals 1 generically, but there's a very similar story for higher supersymmetry. So what you would have here changes a little bit if you want more spinners, but the same sort of technique applies. Other questions? Okay, so this is all, the reason I write this out is that this is something that we can say, sort of with complete generality. You pick your type of string dimensional reduction you want to do. You'll have some SU3 structure, we're aiming for n equals 1 in 4D. Again, I've also done this for 6 compact dimensions, and so this is, SO6 was the spinner I was looking at. If you're doing F theory, that would be a different story for SU4 structure. In the case of heterotic that I've illustrated here, these two torsion classes vanishing, you can show that this is going to be a complex manifold generically. You can characterize, again, for different backgrounds, properties within SU3 structure that you would like, for example, things like this that drop out of certain solutions. So here are the questions then that we want to address. What we want to address are, in this setting, these are the questions, are the set of SU3 structure solutions finite? That's answer to question number 1. So is this bounded? Is it finite? Do they have finite topology? So are there a set of topological integers that may appear in key ways in the effective theory that I can bound? How to build, i.e. what most general constructions could I write down? And the harder question of can I find metrics on them? Which, jumping ahead a bit, of course, the easiest class of SU3 structure manifolds is actually SU3 holonomy manifolds, which are Calabi-Gauss, which I'll talk more about in a second. Even there, which is the easy case, we don't know how to build the metrics explicitly. And this gets much harder for general SUN structure. As I've set it up so far. People have actually looked at that. So a general F-theory four-dimensional background with flux will back-react, the flux will back-react you away from Calabi-Yau towards a general SU4 structure. It's a fourfold, but you do, as I've written this is all specific to threefolds. So you're exactly right that this is, type 2B or type 2A orientifolds and heterotic thus far. There is an analogous story one could tell for M-theory and fourfolds, but I'm not setting that up here. Other questions, comments? Okay. And then something that's going to be very important to us in a moment, topology changing transitions. And this has to do with the idea that there are going to be many possible geometric backgrounds that we could choose. Are we allowed to move between those, either practically in terms of adjusting how the geometry is built, or dynamically in terms of the effective physics, which is, of course, a much more exciting thing. So these are the questions that I want to highlight. Again, these are hard problems, but there has been recent progress, and I want to illustrate where some of it lies, and also where there's obstacles, why certain things have been done the way they have. So 3 rough tools to try to address this. Let me talk about how we're going to try and build SU structure manifolds, SU3 structure in this case. So there are roughly 3 tools for doing this. The first is what I'll call algebraic constructions. And here the idea is very simple. I need to build some mystery manifolds. I don't know how to do it. They have weird properties that I have outlined here. The idea is that I want to choose a simple ambient space. Let's call it curly A. And then I want to write systems of equations equals 0 inside that space. Okay, this is how we build most Calabi-Yau threefolds, and that's not an accident. We'll talk about that in a second. So we would say that X, the space we want, I'm going to call it X3. But in general, this is, of course, a real 6 manifold, is some subvariety of an easy ambient space. That's tool number 1. Let's call it that. Tool number 2, you've already heard playing a central role in Miriam's talk, and here's the idea on this one. Again, I need an easy space to bootstrap my information up on. So in the algebraic context, I have an easy ambient space. I write a system of equations in it, and then I get my resulting space. We're all very familiar with this, even from students when we're learning elementary calculus, right? You want to write down something like a sphere. You pick something like Rn, Cn, whatever. You write down a system of equations in it. Boom, now you've got your solution. For fibrations, the idea is let's have a surjective morphism, I, which takes the space I'm interested in into some easier space. Let me actually not specify the dimension of the space for a moment. Surjective morphism pi, where this guy is the easy one now. So I'm going to encode the easiness in some space that I know about. And I'm going to take my mystery space that I'm trying to build, and I put all the information and how I'm going to build it into a mapping onto the easy space. This we know how to build. Again, classical geometry, lots of examples of complicated spaces with this property. So, dumb example, if the target space B is a circle, there are exactly 2 fibrations over the circle at the level of real manifolds that you can write down. Cylinder says if you have a circle, over every point in that circle, you have an interval. That's the fiber of this fibration. And there's a projection map which takes any point on the cylinder down to a point on the circle. Versus, and here my art is going to fail me, but Mobius strip, let me not actually write it. It's going to be sad. Versus Mobius strip. Right, if you have a non-trivial twisting, that's a non-trivial fibration over S1. These are, again, simple versus complicated space. That's the idea. So obviously, this plays a huge role. We've already seen in things like F-theory constructions where you're parameterizing the axiodilaton by information in this fibration. And also, as we'll talk more about in a second, plays a huge role in string dualities. So the existence of fibrations usually means you have more than one avenue in string theory to get at the same effective physics. And so that is quite powerful as well. And then, just broadly, the last one is surgery. And what's the idea with that? You're going to take an easy space and you want to modify it at higher codimension. So here is my easy space. And now I will come up with a prescription for how to change that space. Say by replacing points with something else, illustrated here as circles/spheres, at higher codimension in the space. Codimension being I don't generically change the space. At an arbitrary point, it looks the same, these two spaces, but at special points, it can look different. This, I should just, again, talk about tools. This is the main mathematical arena for classifying geometries. So as some people might have seen lots about, the so-called minimal model program in algebraic and differential geometry is a huge industry in mathematics for characterizing various manifolds with various topology in lots of different dimensions. The Fields Medal several years ago was given to Kausha Bircher, who proved the finiteness bounded and characterized all Fano threefolds. So these are three-dimensional manifolds, complex manifolds with positive curvature. There's a huge industry in terms of how one modifies manifolds, how one relates them under this. Unfortunately, a lot of it is not directly applicable to string projects in that, in general, mathematically, if you do this process of replacing various higher codimensional structure, you change the topology away from SU3 structure. So do not, but it's still hugely valuable. And of course, this also is going to relate things like conifold transitions, topology changing transitions, flops, et cetera, that are very important in string constructions. So you need to choose these processes carefully. Let me give an example of one that does what you want. So a good one is the so-called small resolution, which is already played a role in various discussions and talks that we've had at this meeting so far. So the idea here is that we have a mapping that looks something like this, some morphism from mystery manifold into an easy space, such that for all r greater than 0, the space of points x inside x easy with the inverse image of little x of dimension r is of codimension greater than 2r. This is simply the statement that you're changing the manifold at higher codimension. So for those of you that have seen algebraic geometry before, this is to be contrasted with the idea of a blow-up, where, for example, you replace a smooth point on the manifold with a divisor. This is something that happens less generically in the manifold, i.e. at a more special point. So resolving a singular Calabi-Yau and a conifold is an example of this. All right, so with those broad pieces in hand, now let's talk about what, again, aiming first for general SU3 structure within these three approaches, so algebraic constructions, fibrations, and then sort of minimal model program, geometric transition/surgery. What is it that we can build? What do we understand? What progress has been made in recent years? So let's start with number one, the algebraic approach. And in this context, what we find is that SU3 structure must reduce to SU3 holonomy, i.e. Calabi-Yau threefolds. Indeed, the only SU3 structure manifolds that are projective, i.e. that they are writable as a simple set of algebraic system inside simple compact ambient spaces that we know about, the only projective SU3 structure manifolds are Calabi-Yau. So CY is unique projective varieties in all SU3 structure. This is to say, again, within the class of simple ambient spaces that you know how to write down systems of equations in, they're all going to lead you to Calabi-Yau. And this is why, because this is probably the easiest and most powerful way we have to write down manifolds, just like it was when we were doing intro calculus, this is why Calabi-Yau is the most studied. So examples of this, i.e. Something like an ambient space which is CPN. I will just write it as PN, dropping the C. You have a set of coordinates that are related by an overall scale condition, homogeneous coordinates. And you write down a simple defining equation, for example, P45 with equation sum on I x I to the 5 for Monquintic, classic first example of a SU3 structure, or indeed Calabi-Yau SU3 holonomy manifold that was written down 40 years ago. You want to write down simple manifolds like this. Various robust data sets of Calabi-Yaus have been written down. In terms of known data, there was the set of all complete intersection manifolds in products of projective spaces. So PNI, PNM. This is the so-called CC threefold set. This was the famous one written down in the late 80s, 7,890 manifolds written down by Candelas and company. And then generalizing this type of scaling relation to more general toric varieties. Of course, toric hypersurfaces. And this is the Kreutzer-Skarka dataset. Max was here in Vienna when he did this work, so fitting that we should be talking about it here. Toric hypersurfaces, unknown exactly how many manifolds live here, but roughly 500 million. So these are some of the numbers that our field has found discouraging, right? Even within this simple algebraic family, we don't know if there's a finite number of these. Already we have 500 million contenders. We've seen, again, from lots of work scanning over such geometries, that there is a huge effort to be understood. What is the physics that we could get out of things like this? Yeah. Good. So the basic issue has to do with the Kähler condition. So let me say a little bit more about these. So Calabi-Yau, as you say, all the torsion classes vanish. I had not said that yet, but Wi's are all 0. Dj is 0 implies Kähler. So where is this coming from? The ambient spaces, if you have algebraic subvarieties of Kähler spaces, they tend to be Kähler. So if you write down simple, compact, complex manifolds that are easy ambient spaces to write down your system defining equations in, they will be Kähler, and then you inherit that Kähler structure from the ambient space that you're working in. Could you write down some weird ambient spaces that were not Kähler? In principle, yes, but actually controlling those to a level that you can then control the systems of equations in them tends to be hard. So this is why this is faltered. If the ambient space is Kähler, then the algebraic system you write down is going to be Calabi-Yau. And so you will end up with this. Other questions at this stage? Okay. Good. So other SU3 structure? Yeah. So that's what I'm about to talk about next. So all the constructions that are legit SU3 structure that people have actually worked with in string theory all come under the fibration category. And that's how people have built them. So let me turn now to those. Actually, let me just say one last thing about Calabi-Yaus before I leave Calabi-Yaus, and then we'll turn to the more general guys. We have a bunch of manifolds, right? But even at the level of manifolds, before we put on other things like fluxes and orientifolds and bundles, we can ask, I have a ton of manifolds, but how much distinct physics do I get out of a data set like this, right? And the answer could be much less. So famous examples of redundancy in this data set, if you're in the type 2 setting, then of course mirror symmetry, which says that pairs of Hodge numbers are interchanged. So roughly half of that data set is reduced under mirror symmetry. You also can try and characterize important topology. So let me highlight this briefly. There is a theorem by a mathematician known as Wall that says that the following topology is enough to sort of specify a Calabi-Yau uniquely. So the Wall's data, we know that I should have said this already, but the vanishing of a first string class, so C1 is of course trace R, being 0. This holds for all SU3 structure manifolds, that C1 is 0. So in the Calabi-Yau context, the independent Hodge numbers, these are just the complexified version of the Betty numbers, excuse me, in terms of D-bar cohomology. And these guys, which are triple intersection numbers of divisors, there is a long vector worth of data, topological data, for a Calabi-Yau threefold that can be written down. And if this manifold, if this data is different, then the Calabi-Yaus are definitely distinct. And it's quite easy to see in most arenas of string theory, for example, heterotic and type 2, that the physics will also be different. However, if the data is the same, so if different x prime, it is x not equal to x prime, if same, then x is equal to x prime as a real manifold, but distinct as complex. And indeed, the Cornell group by McAllister and al. Have just recently shown that Gopakumar-Vafa invariants are different across Walls data pair manifolds. So there is some finer sort of quantum information, even in the type 2 setting, that can be different in those cases. Okay, I wanted that for slightly later. Now let me turn to the question we just had. If we want to build legit SU3 structure manifolds, what do we know about them? And what do we build? So the most genuine SU3 structure manifolds that have been constructed are almost all built as fibrations. So in this context, there are different ideas behind those fibrations. So for example, there is a construction due to Goldstein and Perkushkin, and then Fu and Yao decorated this with bundles compatible with heterotic constructions. It showed that they could build SU3 structure manifolds as fibrations of a general SU3 structure non-Kähler over a K3 surface, that's a Calabi-Yau twofold, with the fiber generically being an S1 times S1. And they do funky things with the way this fiber is twisted to make sure that DJ is not 0 globally. And so this is a genuine SU3 structure. You can write down all the torsion classes for this type of construction. Sorry? No, actually, that's not necessarily assumed. So a lot of people have focused on SU3 structure in trying to make sure the supergravity approximation was good. That actually is going to fail for other reasons. So all of these generically have small cycles in everything that everyone has constructed so far, which is a big limitation. People have looked at sort of mild singularities. And again, getting that in a regime that's controlled is hard. So similar ideas have been constructed where here you have, say, a genus G Riemann surface. Simple object, which is a K3. Here we have a fibration over a Riemann surface such that pi inverse of a point is either a K3 or a 4 torus. So there are nice SU3 structure constructions of this type. What are the pros and cons? So con, I've already mentioned this, all of these have small cycles. Why does that happen to you somewhat generically? Let me illustrate this with the anomaly cancellation condition in heterotic. So in heterotic string theory, you show that DH3 goes like trace, write it this way, trace R wedge R minus trace F wedge F. So very loosely, another bracket there. What's happening is that the cancellation of anomalies in a general SU3 structure background, you have a fixed three-form flux in the background that then is involving a relationship which has alpha prime explicitly in it. So alpha prime doesn't drop out of this expression. In order to actually solve it for a specific bundle and manifold, you end up fixing alpha prime, generally someplace you don't want to be. So in that case, that's the overall volume. You can also, in general, have other small cycles that are in play, and people have looked at these for these constructions. So it's sort of an in-principle problem, which is that the tadpoles tell you that you're going to involve setting scales at places that may not be in the supergravity limit. And then just by accident of the construction, it may be that not all cycles are large. Another issue, though this is getting better, is that we do not have a theorem due to Yao that we even know that metrics exist with the right properties. So you can topologically write down the space, but do you have a metric that will satisfy your equations of motion? This is difficult. There has been recent progress on this, which I think is actually quite exciting. So myself and others have been working on applying machine learning techniques to be able to write down explicit numeric Calabi-Yau metrics. But something that's cool is that those sort of recent approaches to this are working equally well for a general SU3 structure as they are for Calabi-Yau. So this may be something where machine learning actually, not in terms of scanning big data sets, but actually just brute force numeric PDE solving, may be better at hunting for SU3 structure metrics than it was in other contexts. So there's some exciting things there. Correct, yep. So to my knowledge, this is being recorded, so I probably shouldn't say this too definitively, but I am not personally aware of any SU3 construction where people have been 100% certain that they had no small cycles. There could be one in the type 2 setting that I haven't seen, but I don't believe so. So all the coset constructions, Yao, all of these, Goldstein and Prokhushkin definitely have small cycles. This actually has to do with basically the way that you set up, so the way that my collaborators and I set this up, we are training neural networks using gradient descent to minimize loss functions that in the Calabi-Yau case have to do with, if I still have it up, this guy right here actually. So building explicit versions of the holomorphic 3 form in the Calabi-Yau case, you can find pretty explicit constructions of this. You then have, in the Calabi-Yau case, sort of posit Kähler forms that you then try and train towards setting these two equal. This reduces what is in principle a very, fourth order, nonlinear, 6-dimensional PDE down to something that's second order and a lot more constrained. This is the Monchampère type equation. This, as a loss function, works quite well, and it can be generalized to the SU3 case fairly readily. So we did this in one paper. We sort of did a trial run. Just the, why is that working? That's basically just a feature of how we set up the neural networks to approach the solution. Correct. And so, yeah, you sort of, the harder part for the SU3 structure, which I don't have a good solution to, is you need a posit space to sort of set up the whole differential geometry problem on that you want to teach to a computer. So if you have an algebraic Calabi-Yau, then you can sort of give it the points and then start, building this metric that satisfies the differential equation you want. The hard part for, general SU3 structure is you don't even know what space to write down. So we cheated, and we actually built an SU3 structure on an algebraic Calabi-Yau. So we did a non-Ricci flat metric on an algebraic Calabi-Yau background. So it does admit Ricci flat solutions, it can admit other ones. But generically, that's going to be an obstacle, is like, what points are you putting in to do your numeric integration and things. But anyway, just as a comment, I think there is some potential progress that could be made using more modern techniques. And also, a pro, of course, in addition to just being the general case with SU3 structure, is that you will have fewer moduli in general sort of flux backgrounds, of course. So here, these guys, of course, are counting massless singlets in many compactifications of string theory, so you end up with a lot of singlets that you'd rather not have. You have to then, sort of go back and redo a whole calculation in terms of, flux backgrounds and moduli stabilization, as Miriam alluded to earlier. If you do this from the start, you just have fewer geometric ingredients like that to worry about. Yep, so that's one problem. Yep. So if you sort of say, I just threw some random flux in there, like where did I get stuck? It's not going to be at large volume generically. People have bypassed that in certain cases. So there are SU3 structure solutions where they can engineer large volume. But then what has happened is that when people actually looked at that, they end up with other small cycles. So it's just, it's not a claim that there is no way to do that, but just that's not something that's immediate. It doesn't fall out of the construction that you will end up with a good supergravity limit. Oh, I mean, in the heterotic case, H is 0, right? So if, if that's 0, then alpha prime drops out. Flux, then you're going to have that problem. Yeah, correct. Yeah. So as soon as you have a general flux background, then you have to address this problem. Okay. So what I wanted to then turn to is sort of two things. I also wanted to comment on, so here, the genuine SU3 structure solutions are extremely sparse. I gave two, fibration constructions. There are a couple others, maybe 2 or 3 other, approaches in literature, very, very few. So this is something where we really do need new ideas. Being able to approach this with machine learning may be a real regime change, and I am excited about that. But again, in this sort of question of what is possible, if we could even address the sort of simple case of Calabi-Yau, is it actually attainable to say, could we classify all topological families of SU3 holonomy manifolds? Could we show they're finite? This is something that, again, it's the field, people sort of said this is a math question. We're physicists, are we really going to tackle this? But there's actually been a lot of progress in recent years, and I think some degree of excitement in terms of what one may be able to say in that context. So for my last 15 minutes or so, I just wanted to highlight what is the in that might let you try and attack Calabi-Yau. I already used that one. And see if I can not use the squeegee. Be cheeky, this may not work. Okay. So with Calabi-Yau, let's turn to Calabi-Yau threefolds for a moment. And again, the question we want to ask is, what is the generic structure that we can see? Again, with an idea towards being able to say something general about what could arise from string compactifications over this, and then looking towards finiteness and bounding. So in the Calabi-Yau context, like the general SU3 structure, a very big in is actually obtained through fibrations. So clearly, fibration structure plays a huge role in F-theory, as we already heard in Miriam's talk this morning. Importantly, Calabi-Yau n-folds can only be fibered by other Calabi-Yaus. So for example, if you have as complex manifolds an X3, which is fibered over some one complex dimensional manifold, then the fiber over a point is a K3 surface, or worse. If you have a fibration, and this works for fourfolds too, by the way, over B2, then here we have an elliptic curve, i.e. a T2. You can show this has to be true just by the topology of fibrations. So in order to get C1 equals 0, it turns out that your fibers also have to be flat. Important result, which is used a lot in F-theory scans, is that the set of all T2 fibered CY threefolds is finite, and indeed has bounded topology. So we know the maximal bounds on Hodge numbers. This is an old result due to Mark Gross and Antonella Grassi in the 90s. This has recently been extended to almost the same statement for Calabi-Yau fourfolds. So Dicerbo and Sfaldi have proven that there is a finite number of bases, three-dimensional bases for Calabi-Yau fourfolds, and they've also are very close, as I understand it, to proving the finiteness of the whole set. Good. So there's a subset of Calabi-Yaus that we know is finite. This is our major in, actually. Yes. All possible twists over those bases. So you need to show both how the topology changes and every possible fibration degeneration over those. The catch, so proving elliptic fibrations is easy in both cases, so both threefolds and fourfolds, and that's been done already for the fourfolds. The hard part is actually the geometries without section, so the general genus 1. That was the hard part in the threefold proof, and it's the hard part in the fourfolds as well. Okay, so one question we could ask, there's a finite data set of all threefolds. So now you can ask the question, how does that finite data set relate to all other threefolds? So observations that you can make at this point. So these are recent work done by myself, James, who is here, Lottie, who is here in spirit, and several others, is that essentially all, let me not write that, nearly all, and I'll be more precise about this, nearly all CY threefolds in known data sets, i.e. Kreutzer-Skarka, etc., are fibered. So this is greater than 99%. So of all the Calabi-Yaos we know how to build, essentially all of them admit fibrations. They don't just admit one fibration. Generically, they can admit tens or even hundreds of different fibrations. And every fibration that is possible by dimension sort of is there. So if you pick a random Calabi-Yao fourfold out of a hat somewhere, it will be fibered by a Calabi-Yao threefold, by a K3 surface, and by an elliptic curve. Here. I am talking about threefolds, but these studies have also been done for fourfolds. So for the known data sets of fourfolds, which admittedly are sparser than the data sets of fourfolds, then fourfolds are sparser than the threefolds, the same result holds. So again, if you just algebraically make any Calabi-Yao as a complete intersection in some toric variety, this is going to be true. Good. So there is a conjecture for CY3 that in fact every Calabi-Yao, CY3 with H11 greater than 19 is fibered. Do I have counterexamples? Absolutely. Things like the quintic threefold does not admit any fibrations, but that's at low H11. So the result seems to be that as you increase topology, generically everything is fibered. And this is also, similar statements can be made for fourfolds. Good. So this is actually, the statements as written are about T2 fibrations. So they will be, torus fibered, but it doesn't have to have a section. So not elliptic, but genus 1 fibered. Okay. Great. Okay, so what's special about 19? There is a theorem. It's been around for a long time by a mathematician named Wilson at Cambridge, who proved the following. So this is a result by Wilson, who said every CY3 with H11 greater than 19 is either T2 fibered, i.e. it already manifestly has a fibration, or it is contractible to a manifold. I may not say a manifold, it could be singular. It is contractible to one with H11 less than 19. So what's behind this result? It's saying that as you try and make more and more divisors in a Calabi-Yao, so you just dump more and more possible Kähler forms in, generically those Kähler forms are such that their overall volume is not those Kähler forms are not controlling the overall volume. So if you have like a 400-dimensional Kähler moduli space, it's not the case that all 400 of those care about the overall volume of the variety. In general, it means that you have a very Swiss cheese manifold and there are lots of cycles that you can shrink to zero size without affecting the overall volume. When you do that, so if you have a manifold that is contractible, then either you would manifestly see the fiber or you start collapsing cycles down. So the reason this is a conjecture and not a proof, this is almost the right statement to try and prove that everything manifestly greater than H11 will be fibered. And there's actually some concrete work on that. So a proof So this is again by me and James. We wanted to understand, with this type of contraction, this is like a geometric transition, so you want to be able to blow up, make the variety singular, blow it up, and move to a nearby manifold. We've shown that for the 7,890 cc's, and we started this for toric hypersurfaces as well, every manifold is either fibered already, which we can see, that's the 99%, or you can connect to a fibered manifold by one conifold, i.e. you make your manifold singular, you resolve it, this is one of these sort of contraction steps. And in this case, so you're either fibered or you're right next door in the geometric transition sense to a fibration. So you can do it in one step. This is the hint towards how you might try and prove finiteness of all Calabi-Yaus, right? You hand me some random manifold. We can ask, is it fibered or not? We know that there's a finite number of fibered guys, so we have those sort of points fixed in our space of all possible manifolds. Then you can say, if I could modify the topology in a finite number of steps, such that I can make it fibered, then I've got finiteness of everything. So can I come up with a prescription for a mystery manifold in terms of what geometric changes, this is the surgery that I mentioned earlier, what geometric transitions would I make to induce a fibration? If there's a finite number of steps there, then you've proven that everything is finite. And this is sort of where the serious effort in terms of finiteness is going, both in the physics and mathematics community. I'm running basically out of time. So what do I want to say about that? Great. So there's two different ways to do that. So you can actually characterize what it takes to have a fibration in terms of knowing the cone structure and the intersection numbers of the variety. So I don't need an explicit construction of the Calabi-Yau. If you tell me whether certain divisors are effective or not, and I know the intersection numbers, then we can decide whether it's fibered. So there's absolute criteria for that. You can do this in two different ways. So what James and I did for the CC data set is we actually imposed that criteria for all of the 7,890 manifolds using the all possible fibrations. We searched for divisors that could find, we said any divisor that will satisfy this criteria we want to find. Those don't have to be obvious from the toric or ambient description, and indeed some of them are not. That is harder to do for the Kreutzer-Skarka set because of the high numbers of H11 being order hundreds, that's harder. So what Waddy and company did with their searches is they just looked for those that were obvious fibrations that were induced from toric structure in the ambient space. So they looked for fibrations where they could sort of see the projection map happening in the toric polytope. So those are not necessarily all fibrations. They again find like 99% of them. There were some that they weren't able to analyze, and it would be good to go back and do that more exhaustively. Good, okay. So I'm out of time, basically, so let me just leave you with a couple of comments, and then I will stop. So one thing that this sort of, I hope I've eliminated, is this idea of modifying, finding fibered manifolds and then modifying them to make different manifolds, or modifying a mystery manifold into a fibered one is a real in towards trying to prove finiteness. It also, these observations that basically every Calabi-Yau you could possibly make are fibered, say a lot about string dualities. So for example, you need an elliptic fibration in order to use a Calabi-Yau as an F-theory background. You might be like, well, that's a rare thing. Turns out it isn't, right? Basically every Calabi-Yau fourfold you write down is going to be a good background for F-theory. Likewise, heterotic F-theory duality only works if you have a heterotic manifold that has a K3 fibration, or an elliptic fibration F-theory that has a K3 fibration. That was assumed to be very rare. But again, it's generic. So actually, for all manifolds we know about, the sort of string dualities map out a lot of the landscape. So you don't have to do the process of analyzing all possible F-theory and all heterotic solutions in certain cases. Maybe you know that you can actually read off the general answer from both. Question, okay. So I don't want to speak for the whole community. For myself, personally, I mean, mathematicians are going to say it's just not decided yet, and there could be, this could be a fluke of the way we know how to build manifolds that we're seeing this general structure, right? There could be some entirely different way of building Calabi-Yau's or more general SU3 structure that's just wildly different, right? We might have a lamppost effect. That being said, what we understand about sort of the absolute structure of Calabi-Yau's, the criteria that we need, what possible Hodge numbers are consistent, with anomalies in six-dimensional F theory, all these things, I feel like we are actually mapping out the space of all possibilities pretty exhaustively. So my belief is that I think this is finite. I think we can probably prove it in the not, infinitely distant future. And I think we've already mapped out a lot of the possibilities with the known construction so far. But I could be wrong. Other questions? Okay, let me just finish with one quick comment and say that I've alluded to geometric transitions. I didn't have a chance to sort of set those up. I ran out of time, but I'm happy to, if somebody hasn't seen them, I'm happy to talk more about it. Let me just say two things about geometric transitions, and then I will stop talking. So the idea behind geometric transitions, right, this is the notion that you have a smooth manifold. You move to a point in moduli space where you have a singular variety, namely nodal, and then you resolve those singularities. Another important property of Calabi-Yau's is that there has been conjectures by mathematicians, namely the mathematician Miles Reed, that all possible Calabi-Yau threefolds are connected by geometric transitions. So irrespective of construction, there are processes like these, i.e. conifolds, that you could do to connect all possible. This is recently, mathematicians have actually been exploring this structure in the context of more general SU3 structure and connecting Calabi-Yau threefolds to SU3 structure varieties. So you do a geometric transition where you screw up the global Kähler structure, and then you end up somewhere different. There's been a lot of recent work on using geometric transitions to probe this, and again, there are conjectures that every SU3 structure manifold is connected by geometric transitions. That would mean that every possible string compactification on such a variety would be linked in some field space, i.e. possibly even dynamically. This is important, and there have been recent results that show that the sort of, the wildness of how non-Kähler these manifolds can be is actually constrained by the processes of geometric transitions themselves. So there is a recent result by a mathematician named Friedman at Columbia, who showed that if you have any SU3 structure manifold that can be connected to a Calabi-Yau via a geometric transition, it is what's called cohomologically Kähler. So it has very simple properties on its two-form J that you can write down. So there's a lot of interesting work, again, in terms of bounding possible geometries based on this structure of geometric transitions. So I have more I could say. Yeah. These are hard to write down. I can't write one explicitly. I mean, they're very formal, but Yau has some. So Yau has a really weird one that actually connects known Calabi-Yau threefolds, algebraic ones, to products of S3s. They're weird. They're like these weird twisted S3 products. But I can give you a ref if you're interested, but I can't write those down very explicitly. So certainly, yes, these are related concepts, and mirror symmetry is believed to extend outside of the Calabi-Yau case into certain cases that you mentioned. I believe also these sort of T-fold constructions. I mean, you don't even have to stay in geometry, right? So you can even use T-duality rules in the transition functions to patch things together that may not be regular manifolds anymore. So I believe that yes, you can play with T-duality rules across more general SU3 structure, and you can just leave geometry entirely behind. So yeah, I'm happy to, I'll be here in a couple more days. I'm happy to chat with anybody if there's any geometric questions that have arisen in this talk. And otherwise, I'll stop here and we can discuss more tomorrow.